Okay, so I got a question of how to determine if a molecule is polar, and how can I say water is not symmetrical, right? So if an H2O molecule, why do I say it's non-symmetrical if I can draw a pretty little line down here and it looks the same on the left and the right? Okay, what I told some of you to imagine with a particle or a molecule like this versus like this is that you can see, obviously this one, if I go up or down or left or right, I can draw like axes of symmetry in all directions. It will be nice and symmetrical. Okay, that's good enough for molecules like this to understand, and for this one to understand there's nothing above or below, and there's the same thing to the left and right, so that's good. This water molecule, you can then say, okay, it's got two things below, nothing above, so it's not symmetrical because above and below are different. But it's not really good enough to explain fully because there might be things like this where we don't know if it is necessarily an alright distribution of charge. So what I actually mean by symmetrical is symmetrical refers to the distribution of the charge. If there's an asymmetrical or symmetrical distribution of the charge, then there must be like a balanced, even distribution of charge. So we have to look at dipoles and electronegativity to do that properly, and I'll show you in a second. But what we can establish already is that even if I don't have molecules, if I just draw a random little shape, okay? So like in grade, whatever you encountered it, 8 or 9 with maybe in 10, with polarization, where we might induce a positive and a negative side to an object, we can say that one side would be slightly positive and the other side would be slightly negative because it has like more of it, the pluses over here and more of the negative particles over there, right? Okay, so in the same way, our bonds, when we form something like HCl, we calculate the change in, or the change in electronegativity, so the difference in electronegativity. So between chlorine and hydrogen, we can see chlorine is much more electronegative, so it's a polar bond, and then therefore the electrons shift in that direction. So we have a dipole. The positive side is this side of the arrow, and the negative side is that side because our electrons shifted to there. So if we look at this molecule as a whole, if I just look at this and say, okay, that's my molecule, one side of the thing is negative, the other side of the thing is positive. This is not a symmetrical distribution of charge. Okay, I can find a side that's more negative and a side that's more positive. So this is polar. Whereas if I compare it to something like CO2, okay, there are polar bonds in here. Okay, CO2 has polar bonds. Okay, we can say this side is more negative, this side is more positive, right? The electrons shift closer to that side and closer to that side. Okay, cool. So we know that the bonds itself cause like little dipoles to form, and this side is more negative. But if we look at the molecule as a whole, right, the middle bit of it's more positive, this side is more negative, this side is more negative. Okay, that's like an even distribution of charge, more or less. Both sides have the same amount of negative, it's positive in the middle. We can't go and say, okay, it's got one side of the molecule is positive, one side is negative. It's not really the case in this one. So I'll show you now a way to see it even more clearly, but that's the idea with symmetrical distribution of charge. If we have CH4, even though it has polar bonds, we can see that even if all this becomes positive, 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 and slightly negative there, it's positive all around, right? So if it was just like a circle, it'd have positive here, positive here, positive here, positive here. It's not polar like this one. The ones that are polar are more like a magnet where one side was north, one side was south. One side is plus, one side is minus. So for instance, something like this, okay, and it's actually 3D shapes. I'm just going to draw the 2D version still. You don't need to stress about that. If we say all of these sides are slightly more negative, for instance, right? And because it's a polar bond, so the dipole is in this direction, this side would then be slightly more positive. Okay, what happens if I actually look at this as a little molecule like this? These three negatives at the bottom, so it's obviously more negative at the bottom. There's a positive at the top, so it's obviously, or induced dipolar partial charge at the top, so it's obviously more positive at the top. Now it's not an even distribution of charge. I have one side that's negative, one side that's positive. So that's what I'm actually looking for. Okay, and to determine this, luckily we know how to add vectors. So we can even view these partial charges, these dipoles, as vectors, right? So let's do it with 3 examples. So I'll redraw them quickly, and then we'll look at water to see why it's polar by looking at its dipoles. We'll look at that CH4 or CO2, for instance. Yeah, let's do CO2, and then we'll do our little buddy that isn't maybe as easy to see. Okay, so now we can look at these. Let's start with water, since the original question was about water. Let's draw in the dipole. Which side is more positive? In which direction does my electron shift? Like this. So this is slightly more positive, that's slightly more negative. And the same thing happens over here. Okay, so slightly more positive, slightly more negative. So you can see one side of the molecule would then be the top slightly more negative, the bottom would be slightly more positive. So there would be an uneven distribution of charge. The molecule is asymmetrical because it's positive side at the bottom, it's negative side at the top. We can see this as well by saying, imagine these two things are vectors. If I add them up, okay, so I'm just going to, let's do it at the top so you can see it's for this one. It has one vector going this way, one vector going this way. So in which direction does this shift in electrons actually do? If I add them up, the net, right, so this is my resultant, is going to be an upward shift. So there's a resultant dipole that says the top is negative, the bottom is positive. The electrons are at the net going to be shifted to the top of the molecule. Okay, if we view this then, for this one, okay, this is the same type of thing. I'm just drawing in my dipoles quickly. So all of them shift the electrons down. If I add up those things as if they were vectors, this one and that one, what happens if I add a vector to this direction and one the same size to this direction? They cancel out to a 0, right? And the same for the top and bottom. It's 0 net. So if these things add together to form nothing and nothing, there is no net dipole. So it's non-polar. For this one as well, we can see that even though there is 2 dipoles, what happens if I add a vector to this direction and one to that direction, right? So this one and that one, they add up to 0. There's no net dipole. Okay, and for this one, so there's symmetrical distribution of charge. For this one, I can look at this is the direction my vectors would add, and we can see that even though it shifts electrons to the top, it also shifts them to the bottom in some way. And if I were to add those vectors together, we can see it would be like equilibrium, right? They would add up to 0. So I'll just label them. This is vector 1, this is vector 2, and this is vector 3 over there. So if I add them, 1 plus 2 plus 3, equilibrium, it's a 0 net vector. Okay, so actually this is also non-polar because there is no net dipole formed. Okay, so symmetrical distribution of charge. This side is more negative, that's more negative, that's more negative, but it's all around the molecule. There's no positive side of the molecule and a negative side of the molecule. Even distribution of my charge. So this is how to determine if things are polar or non-polar for molecules.